No, we did have Justin tell us last time the other things about Fiat Shamir that could be like security considerations. Okay, we're good. Welcome, Daniel.
Thank you.
And thank you for accepting our invitation to talk about Nexus and what you guys are doing in
More than happy, yeah.
zkVMs. Go ahead.
Excellent. Yeah, so hi everyone. This talk is going to be a little bit different. Previously Jens gave a pretty technical talk of our new memory checking mechanism that is part of the Nexus 2 machine, which is fairly more exciting and interesting than the Nexus 1. My talk is going to be about the Nexus 1, and it's going to be a little bit more product focused. So you won't see many equations, but at a high level, it all makes sense. And well, it's all based on open papers, especially on the folding scheme literature. So I think this will be just another flavor of a talk, and hopefully, it will pick a little bit on your brains, but not too much. So at Nexus, what we're trying to build is essentially trying to build like a next generation zero knowledge virtual machine, sort of like inspired by the TinyRAM architecture, right? And essentially the goal that we're trying to solve is, okay, before I dive into that, this is just like the brief agenda. I'm going to give everybody a high-level overview of the Nexus 1 machine and its architecture. And then I'm actually going to talk a little bit of the technical details on the prover. So our goal is, can we build a machine that can prove at an extremely high rate, right? We say just bluntly, 1 trillion CPU cycles proved per second, or hertz, right? And well, there are two ways to achieve this, right? Can we prove more CPU cycles per second with the same resources, number one? And number two, can we allocate more computing power to this machine? And so the Nexus project attempts to combine these two things together, right? Like how can we make ZK more efficient, and how can we allocate more compute to it? We have a white paper online on our website, nexus.xyz. That explains the architecture of the machine. And first of all, let me say that this is all open source, MIT license. So you can use it, you can try it out. In fact, it's super simple to use. And sort of like the purpose of this talk is to say, hey guys, we built this. It's totally free, it's open source, you can use it. And the components that we use to build this machine are also very utilizable. It's very modular, so if you want to build any other project, you can do it with our code base. So sort of like the goal is, how many computers can we get together to compute a proof? How much compute power can we aggregate to compute a single proof, right? And so the goal here is, can we prove a really, really large statement across many, many machines? And so we recently open sourced the Nexus 1 zkVM. And there's sort of like a hidden implementation of the Nexus network there that essentially, technically, what we are building is a PCD network, right? The generalization of IVC. And so we're trying to bring a lot of these research papers into actual implementation, into a real-scale technological system. And it's largely a systems problem as well, not only cryptography. So as mentioned, it is open source. And it's just about reducing the cost of ZK through many techniques, not only new cryptography, but also engineering, hardware optimization, et cetera, et cetera. This graph is talking about the relative cost of verifiable computation compared to normal computation. So our goal is, can we achieve an order of magnitude performance difference in the cost of ZK, right? From something from 10 to the 6 today to 10 to the 1. And there is no theory bound why we shouldn't be able to achieve this. Alternatively, another way to phrase the problem is, can we build a zkVM that just goes all this way up to 1 trillion hertz in speed? And so we think we can. We think we can do it with enough compute power and with enough innovations. So some of you might not be very happy with this slide, because it it omits a lot of things, and it's designed to make it look a little bit convenient for the story that I'm trying to say here. But recently, right, we've seen this, oh shoot, sorry. We've seen this innovation on the folding scheme type of literature. You guys have all seen it, from nova to cyclefold, supernova, hypernova, et cetera, and previous constructions. And a lot of these papers are like propose just highly efficient recursion systems for building IVC and PCD. So, just wondering where history is going to take us. Maybe folding is this, we've actually implemented folding, and it has some downsides to it, of course. But like, where will the community go within the next year or the next 2 years? Where will the industry go in the next year or the next 2 years? How powerful will these proving mechanisms be? How much computing power can we get? And so, essentially, the Nexus project is a bet on our intellectual capabilities, let's say, as humanity, and computational capabilities in terms of infrastructure, to just build a really, really, really powerful prover that can be really production ready for a lot of applications. So bringing a lot of the theory to actually exist. And so what we say is that, like some of you might be familiar with this, like we have had like Groth 16 proofs for many years, right? We've used Halo 2, like the PSE fork, et cetera, many times. Those two are likely the most widely used proof systems today in production deployed systems. And what people are doing to scale them is just throwing added GPUs, FGPAs. Yes, there are some innovations in other parts of the universe, but they will only give us a 10x in performance improvement. They won't give us a 1,000,000x in performance improvement. We can't go from 10 to the 6 to something like 10 to the 1 just by hardware acceleration. I mean, this is obvious, but it's not obvious to everybody. What we say is that we need innovations on theoretical cryptography in the architecture of zkVMs and proving mechanisms. So how do we go beyond? So our first attempt, and I will be honest with you, the Nexus 1 is very far from reaching this goal. But the question is, how can we have like a progressive sort of like improvement towards achieving this goal? And our first take at trying to build a zkVM that reaches 1 trillion hertz essentially adds a lot of further structure to what a traditional zkVM is usually considered to be. So on the left-hand side here, we have what we call the traditional zkVM structure, which is essentially combining a snark with a universal circuit, as proposed by the TinyRAM paper. And so you just put like a lot of CPU cycles together into single batch, and then you just prove it with the snark. On the right-hand side, we have essentially the added components to the machine that we have for this Nexus 1. And so it's actually, we have more. So at the top, we do have a snark that generates the final proof. But before we generate this final proof, we do this parallelized proof generation that accumulates proof in a tree-like fashion, as it has been proposed in a few papers. For example, Carla here, she has a paper on that topic. And this has been proposed in some of the other papers that I linked to on the history of ZK back then. And so essentially what we did is, OK, what if we bring these papers like the hypernova, nova, and kilonova, we implement them from the ground up using artworks, and we actually build this proof accumulation tree system, and have a bunch of machines actually collaborate to generate this proof. And so we did it. And the bottom layer is the execution layer, which is the layer that extracts the witnesses before the proofs get aggregated. So this is what we call the Nexus 1 machine. And so as mentioned, the machine is actually fairly slow still. It goes at about 100 hertz. 100 CPU cycles per second, right? So we're a few orders of magnitude away from our goal. This is as measured on an M2 MacBook Pro. But importantly, if we unite many M2 MacBook Pros together, we can further scale this compute. So the analogy that we like to tell to people is that right now, the architecture of zkVMs is super simple, sort of like how neural networks were back in the day. Maybe what we need is further structure for zkVMs, such that further parts of a zkVM architecture are optimized individually, leading to a more rich structure, such as what has happened with convolutional neural networks. Sure, the analogy, I mean, there's no reason why it should be true, but we think it is true. And as how we're thinking about the Nexus 2 and the Nexus 3, etc., we think we will see more and more components. So first, all of these things have been implemented in our open source, and all of you can use it, and you can test them, and you can benchmark them. So from the ground up implementations of all of these systems, the Zeromorph PCS, the Spartan modified Spartan CK Snark on Arcworth, the Cycle Full Scheme. Hypernova was open sourced about 2 weeks ago by Sam here, who's on the audience. Oh, there you are. Yeah, he implemented Hypernova. These are the first from the ground up implementations of this folding schemes, besides the prototype version of Microsoft Research. Well, so essentially what we do is we have a 2-cycle of elliptic curves. Those of you who might be familiar with the NOVA and Hypernova papers, etc., right? Essentially, one needs to operate over that 2-cycle of elliptic curves, and that's why the cycle fold paper was proposed. But importantly, we need to do this in the distributed setting amongst many machines. So every machine is actually sending 2 different proofs, a proof over the primary curve and another proof over the secondary curve. Logically, sort of like the argument that one can make to using folding as opposed to other systems is that there is a trade-off in proof size that is happening. Folding proofs are way larger. They are like a few megabytes in size, but they lead to low recursion overhead. Concretely, for example, Nova has about a 10K constraints in recursion overhead, and it increases beyond that, but it leads to highly efficient recursion. Now, there are some problems into why the very first version of the machine actually goes that slow. And the reason is the universal circuit that encodes the CPU architecture is actually fairly big. It's like 30,000 constraints, which is pretty big. But our second version of the system will further reduce that size. So because we make this trade-off improved size, and we are interested, because of industry applications, in making these proofs compatible with Ethereum, we have to put it into what we call a compression sequence. And actually, this has sort of like evolved through time. But the first step in the what we call the proof compression system is an application of the modified Spartan construction for relaxed R1CS. Then we apply a recursive step with Halo 2. And finally, we apply another recursive step with Grot16, which gives us the Ethereum verifiability. Out of this 3-step compression sequence process, what you will see on the GitHub code repo is essentially the first 2 steps. The last step is missing, but that will be completed soon, hopefully. And this is essentially our very first version of the proof compression mechanism that will hopefully be further improved for the Nexus 2 machine. And for the Nexus 2 machine, something that we expect to have.
For Nexus 2, are you subscribed to all the security conversations happening in the different schemes? Because you're basically affected by every single one of them, right?
Oh, pretty much.
Okay.
Yeah, we are affected by all of those. Well, anyway, I'll defer that. So just like to not spend too much time here, we get inspired by Tiny RAM. Right, the question, can we design a CPU architecture that is optimized for proving performance? So we call this the Nexus Virtual Machine 1. It's inspired by RISC-V. It's almost the same as RISC-V, except with some minor edits that allow us to do cheaper instruction decoding. I won't dive into the details here, but another part of the product itself is the ability to extend the CPU architecture with custom instructions, right? And so in the context of IVC unfolding, this was introduced by the Supernova paper, right, which essentially shows how to do non-uniform IVC, wherein the cost of proving each step is only proportional to the cost of proving the individual instruction being proven. And so in practice, this allows us to further optimize things with this precompiles, which is becoming a little bit more of a popular concept nowadays, but it's a really important consideration for developers to be able to have precompiles for SHA-256, KCHAC-256, CCDSA signatures, etc. And so we have a problem, and this problem is that, as I am mentioning, we have two systems, one that is for IVC, so like straight line, and a second one that is for PCD, so like tree-like structure. And Supernova is pretty much only compatible in the, with the IVC setting, but it doesn't work very well in the tree-like PCD setting. So we actually have two modes of the machine. One that is like straight if you don't have multiple machines, and we use Supernova. And the other one that is like parallel if you have multiple machines that are untrusted, and we use Hypernova for that. So importantly, the whole point is like, can the user experience be such that you don't even realize that there is a zkVM, right? Can you, in just a single command on a new ROS project, be able to generate a proof?
Sorry, your user is a Go developer.
It's a ROS developer.
ROS developer, okay.
Exactly. So how it works is you generate a new ROS project, and you install a zkVM, and just using cargo Nexus proofs, you generate a proof, and cargo Nexus verified, you generate you use the verifier. And we think it should be that simple. Like, you as a developer shouldn't know everything that's going on behind the scenes. So this actually works. This is the important thing. At least it works. Sure, maybe it's not super fast as how we want it, but it works. And so the rest of the work that we're doing is, how can we individually optimize each of the components? The CPU architecture, the proof compression system, the prover mechanism for IVC and PCD, the memory checking mechanism that Jens presented here, the compiler, which I didn't talk about, which leads to further performances, and the system that extracts the weaknesses, which actually becomes a bottleneck at when we're talking with high throughput computations. And so just diving a little bit into the detail of the prover specifically, sort of like the goal is, can we do recursion without snarks? And the reason why we would want to do it without snarks, perhaps not a super in-depth discussion, but is sort of like the promise of folding is very low recursion overhead, very low memory consumption because of the IVC setting, and only and a very good prover in terms of that it's just one MSM per step. However, we've implemented this, and it's still fairly slow. And I think a lot of people were excited about folding. We are excited about folding, but folding has some problems here and there, especially because of the 2-cycle of elliptic curves and the MSMs. So, well, it happens that when you actually implement something in practice, not everything works as you expect, right? But at least we have learned and built some infrastructure that allows us to do just general recursion and PCD, etc. And we can actually switch the prover with other better proving mechanisms, as we've seen from, we've explored as well, like, for example, the BNews type of literature, as well as just generally Starks, etc. There are multiple considerations there. But how we build the Nexus 1 prover is by actually implementing cycle fold and a couple of folding schemes. In particular, the traditional folding scheme for R1CS, Nova, but also the multi-folding scheme for CCS. And so we have two provers, Nova and Hypernova, and two generalizations of those, parallel Nova and parallel Hypernova. The reason why we're interested in CCS is, as you may know, so that we can prove R1CS Planck-ish in air. Reason being, for example, encoding Poseidon circuits in Planck-ish is just way better than in R1CS, and so on and so forth. Yeah, I just explained the benefits of CCS, which all of you should know. So yeah, this is actually also we believe the very first actual implementation of cycle fold for doing just foreign arithmetic on the second elliptic curve. However, part of the question is, like, will the future be still cycles of elliptic curves, or will it be like hash-based snarks, right? And where there's just only one curve. I guess we will see. I already explained the precompile system, but how it operates is it's actually perhaps not as how you might think. So we have this like ASIC-like type of circuits that extend the instruction set and the CPU circuit. But the CPU circuit is actually multiple copies of the CPU circuit as one supernova channel. And the reason is the recursion overhead is probably too large for just one CPU cycle. So the question is, how many CPU cycles can we pack in this leftmost supernova coprocessor, so to say? We call it coprocessors because that's sort of like the term adopted in industry, but it's synonym to precompiles. And so part of the question as well is, how can we encode the CPU circuit into an even smaller circuit so that we can pack even more instructions? And if you are familiar with the Jolt type of literature from Justin Thaler and other such schemes that use lookup arguments, that as well allow us to pack many more cycles per proving step. Well, yeah, so bottom line is we literally implemented this. This is a screenshot from the white paper, which pretty much just follows a Hypernova paper. So we did implement Hypernova. We did implement Nova. We did implement CycleFold. It's all here. As you can see, this is a GitHub screenshot. So you can play out with it if you want. And so, for example, in just this like folder, we will keep building more proving mechanisms and experimenting with more of the things that are being innovated in the space, etc. And so just a summary of the Nexus 1 IBC prover is, yes, it has fast recursion, very low recursion overhead along the lines of the Nova paper. It is pretty correct. Low memory overhead, that's also because Nova uses very low memory. Because we have Hypernova, we can prove CCS instances. The proof compression mechanism essentially works with just a wide variety of snarks and starks that this can be composed with. And we do have an implementation for a specific sequence of that. And it's very parallelizable because of the MSMs. So one can, as you know, parallelize MSMs on GPUs and FPGAs and all that. However, we have a few downsides that are actually fairly bad. And number one is that the engineering for implementing these folding schemes is pretty hard because of the 2 cycle of elliptic curves. Not only hard, but error prone. And so this is bad, right? Number two, yes, big fields, right? So we can't take advantage of the, the CPU architectures being optimized for U64s, et cetera, et cetera. So this does lead to sort of like a fundamental problem with Pedersen commitment-based provers. The common reference string for Pedersen commitments, so the Pedersen basis, we wouldn't need this if we were using Starks, but we do because we're having MSMs. In practice, this is not a huge problem, but it is a little bit of a problem because it requires some trust in the mechanism, right? And we wouldn't want that to be the case. And largely, but very importantly, is there exists a large communication overhead between the provers. And the reason is, right, the Nova proofs are large. So it makes sense within a cluster of machines. We've tried multiple like systems tricks to optimize that, like recomputation and other such things, or have trees with different topologies. However, the communication is still quite bad. And so part of the second version of the architecture that we're building is compressing the proofs with a snark before they're sent over the network to further reduce the communication overhead. So the Nexus 2 system essentially reuses some of these components and throws some of those away. And for instance, it includes the new memory checking techniques that Jens presented yesterday. So I mentioned that the CPU circuit is pretty big, like 30,000 constraints. It happens that 90% of the size of the circuit is because of the memory checking mechanism that uses Merkle trees, which is log of n, right? And so our hope is that we can drive that cost to O of 1 and reduce by 10x the size of the circuit, which would give us about a 10x improvement in performance. Then with further arithmetization tricks like Jolt, we think we can go way higher. So the bottom line here is that, yes, we've implemented a lot of this. It works. It is fully pluggable everywhere. Perhaps it's not ready for a production grade usage today, but it's the very first version of the machine, and it's free, and everybody can use it if they want. And yeah, it's free for anyone. And yeah, that's pretty much it. So excited for you guys to check it out.
Thank you, and thank you for implementing some of these themes and open sourcing them. So I'm interested in your future roadmap. You want to get a 10 to the 6 improvement. So by the time you've got to, say, Nexus 6, will these machines have seen things that us people would never believe? And since they're ZK, will the witnesses be lost in time like tears in rain?
Yeah, that's...
You probably had
I know that reference.
No, seriously, how are you going to get a million times improvement?
Yes. So to my surprise, and I usually like to say this, I am less optimistic than the rest of my team. Like Jens is more optimistic than me about our goal to getting to something like 10 to the 1. And that's a Blade Runner reference I just remembered. I love that scene. So first of all, we think that we can get a 100x improvement in performance by a 100x reduction in the circuit size alone, coming from the new techniques from Jolt. And we've been following this very, very closely. And this is a serious breakthrough in just the architecture of zkVMs using lookups. So that's pretty serious. That's a couple of orders of magnitude, sure. There is a lot of work on, so number one, the memory checking system that further gives us like a 10x in performance, hopefully. We think that another sort of like level in the, so at some point, like the precompiles play such a central role that measuring speed by CPU cycles per second stops losing meaning because like the actual step that you're taking, like it differs in size, right? So what do you use for measurement there? We are developing a set of libraries for a wide variety of precompiles. So the whole point is that the architecture of the machine will be is modular. So we can use the benefits of special purpose proof systems, like for example for matrix multiplications, that are not that don't use like this general purpose computational paradigm. And for example, with matrix multiplication, the most efficient proof systems out there have like a 3x overhead over just normal computation, right? So this is less than 10. So can we use a lot of the special purpose proof systems to accelerate special common instructions in the zkVM? We think we can get there and have a software system that is also like, well, really nice to use, etc. So those are ones. Sure, also proof aggregation is something that I didn't explain here, but it's also really easy to do. Proof aggregation doesn't help us in terms of prover performance, but it does help us reduce the cost. And at the end, at some point, it's not only about the computational cost. At some point, it's also about the economic cost, right? And so how can we make the economics of the whole system better? So that's sort of like the roadmap there. There are more things. In the side of hardware acceleration, right? You know, the folks that have been working on Binius have been working on that, and that gives a further 10x improvement because we can use like SIMD instructions in FGPAs. So that's another route.
You didn't mention light. At some point, you'll calculate all this with just light working with itself, but that would be an improvement for everybody else as well, right?
Yes, exactly. Yeah, thank you. Amazing question. Yeah.
I have a rationale question for getting to 1 trillion hertz per second. I mean, running the computation itself is like, you know, you're going to take only 1 billion cycles or even 3 billion cycles per second. No, I mean, is there an application? And also, where do you start measuring your speed if you want 1 trillion? Because the computation itself is going to slow you down. So, I mean, isn't 10 to the 3 enough? Like, for example, it'll be twice the computation size.
Interesting. So is your question about like in which practical case would we actually want a trillion CPU cycles per second?
And where do you measure this trillion? Like, it must be after the extended witness is generated,
Yeah,
right?
exactly. Right. So sort of like the main, I think, use case that we see just in the foreseeable future, right, is on the side of, well, ZK rollups naturally, right? And those computations, each block is about 1 billion cycles. And so we envision a future for Ethereum where there might exist like 1 million ZK rollups computing in parallel, right? And so this will require proving like 1 million blocks per second, which goes beyond like the trillion hertz. So that is sort of like the future that we envision, but hopefully we can think of outside the blockchain, right? Like ZK has been used in the blockchain many times, but it hasn't been brought to outside the blockchain as well. And so our hope is to further improve the industry in that direction. And so just like parsing a JSON file is a program that takes millions of CPU cycles and gets close to billions of CPU cycles if the JSON file is sufficiently large. So it's really easy to get to 1 trillion hertz. So I actually think that 1 trillion hertz is probably too low. But yeah, I guess we can dream big all day, right?
Okay, thank you very much.
Awesome. Thank you.
Thanks, Daniel.